Hello everybody, and once again welcome to my channel. And in this today's session I am going to, as you can see on the screen, we are going to start with a series on gravitation and electrostatics. Okay, so this is something struck me, and I thought that gravitational and electrostatic, these are two different units in Ibdp. Okay, so I wanted to see that students are getting to learn both this electrostatic and gravitational uh, forces, fields, potential, etc. together simultaneously. Okay, so that was the idea behind this series, and whatever and everything that is common between these two concepts of gravitation and electrostatics. Okay, there are so many things common among these two. Okay, so that I am going to discuss, and we are going to study gravitation and electrostatics together. Okay, so I hope this will help students who have studied both the topics separately. Okay, and if they have not understood properly, when you do a comparative study, or when you do a simultaneous study of both the topics, it becomes more easier. That's what I strongly feel. So let us get started with this series on gravitation and electrostatics, and today being the part 1, and in this I'm going to deal with the forces. Okay, only the forces part of this gravitation and electrostatics, right? So as you know, this gravitational and electrostatic, these are the two different fields, you can say. Okay, they are the two different fields, right? And they have their own concepts. Gravitation has its own concepts, electrostatic has its own concept, but then all these concepts are very much matching. Okay, they are very close to each other, and that is why I thought I will go for a combined study of this gravitational and electrostatic fields or forces or whatever, right? So to start with, we'll talk about gravitational and electrostatic forces, right? Now the first thing that I want to mention in this regard is any field, okay, whether it is gravitational field or electrostatic field, okay, these fields always give rise to forces. Okay, so whenever any particle or any object is placed in the field, it is bound to experience some force. So in a gravitational field, a particle will experience something called gravitational force, and in an electric field, a particle will experience something called electrostatic force. So gravitational force will be denoted by Fg. Okay, this is a force, so it is a vector quantity. This I am going to write as gravitational force. Okay, same way, electrostatic force I am going to represent by Fe. This is also a vector quantity, and this is electrostatic force. Okay, as I told you, these forces exist in certain fields. Okay, so gravitational force you will find in gravitational field. Okay, and electrostatic force you will find in electrostatic field. Okay, now suppose you have a mass capital M, and you have another mass small m, and these two masses are separated by a distance, say r. Okay, then between these two masses there is always a force of attraction, okay, which is known as Newton's gravitational law of forces. Okay, so Newton's gravitational law of forces always says that between any two objects, okay, of having some mass, okay, like in this case capital M and small m, these are the masses of the two objects separated by some distance r, will always experience a force which is known as force of gravity or gravitational force, and this force is proportional to the product of the two masses, that is m into m. Also, this force is inversely proportional to the square of the distance between them. Okay, so the distance between them being r, so force of gravity will be proportional to 1 by r square, or inversely proportional to r square. Combining these two, you get Fg proportional to capital M small m upon r square, and if you replace this proportionality sign by a equal to sign, you will get a constant called G, and Fg will be equal to G capital M times small m divided by R square. So this happens to be the formula for, and this being vector, okay, you have to put the arrow mark on top of it. So this is a final formula for gravitational force. Fg is equal to G capital M small m, that is the product of the two masses, divided by the square of the distance between them. On the same ground, okay, you can define electrostatic force. But in electrostatic force, okay, you are not going to deal with the masses, but you are going to deal with the charges. Suppose you have a charge q and you have another charge small q. Okay, these two charges are say these two charges are separated by some distance, say r. Okay, similar to this concept. Okay, then again here the electrostatic force, that is Fe, will be directly proportional to the product of the two charges. Okay, so it will be proportional to q times small q. Okay, also this electrostatic force will be inversely proportional to the distance between the two charges, that is r square. Both combined, you can write Fe is proportional to q small q divided by r square, and this can be written as Fe equal to, now we are going to put a constant called 1 upon 4 pi epsilon. Okay, this is a constant, and then of course your capital Q small q divided by r square. Now here you have to take care of what this epsilon means. Now epsilon is known as permittivity of the medium. Permittivity of the medium. Okay, and this 1 upon 4 pi epsilon 0, if you take epsilon 0 as the permittivity of air or say vacuum, if epsilon 0 is the permittivity of air or vacuum, then 1 upon 4 pi epsilon 0 is a quantity represented by a letter called K, and this K is called as a Coulomb's constant. Coulomb's constant. So here you have to bear in mind that these forces, that is electrostatic forces, they are not the same for all the medium, because as the medium changes, this force value will be affected. So the epsilon, that is the permittivity of the medium, is always taken into consideration. For example, the permittivity of air you have to take as epsilon 0, and 1 upon 4 pi epsilon 0, this quantity totally is known as K, that is known as Coulomb's constant. So this Fe, for electrostatic force for air or vacuum, can be written as K capital Q small q divided by r square. Okay, so this is the formula for vacuum. Okay, when you are talking about vacuum or air, right? So you can see a striking similarity between these two formulas, gravitational force and electrostatic force, right? What is the similarity that you see? Both the forces, this gravitational force is inversely proportional to the square of the distance between them, and the electrostatic force is also inversely proportional to the square of the distance between the charges, right? Of course, the unit will be newtons, okay, for force as usual. I don't want to mention that, but in the gravitational force, on the numerator you will find the product of the two masses. Capital M is the mass of a bigger body, small m is the mass of a smaller body. You can take that way, not necessarily, but generally capital M is the bigger body, small m is the smaller body, right? Here capital Q is a charge which is normally known as a source charge, and small q is a charge which is known as a point charge or a test charge, right? And in this case also capital Q is bigger in size as far as its magnitude is concerned, and small q is smaller in size. Okay, fine. Now these are the two formulas for the forces, the gravitational force and the uh, electrostatic force. Now striking point I want to write about this gravitational force is G is equal to, the value of this G is equal to 6.67 times 10 raised to a minus 11. Okay, and the unit of this is Newton meter square per kg square. Okay, and this G is known as a universal gravitational constant. Now why it is known as universal gravitational constant? Because this G as a constant you will be using for all the medium. Okay, so in any medium you go, this G is going to have the same value. Now same is not true over here. For electrostatic force, the value of this constant will keep on changing. Okay, because if you go from one medium to another medium, the force will not be the same. The electrostatic force will not be the same. Okay, so here your force is dependent on the permittivity of the medium. Okay, the permittivity of the medium. So basically the permittivity of the medium is denoted by a epsilon in general. Okay, let me give you the value of epsilon 0, that is the permittivity of the air or the vacuum. Okay, that is taken as epsilon 0. So epsilon 0 is epsilon for air or vacuum. Okay, and this has a value of around 8.8. Okay, 8.85 multiplied by 10 raised to a minus 12, and the unit here is Coulomb square per Newton meter square. Okay, one more if you want, epsilon for water, okay, is equal to around 7.8 times 10 raised to a minus 10 Coulomb square per Newton meter square. Okay, so epsilon value will differ for different medium. Okay, and accordingly the proportionality constant, that is K, will also differ. Okay, so basically electrostatic forces are dependent on the medium, while gravitational force is not dependent on medium. It is same in all the medium. Okay, one more thing that I want to tell you about this gravitational force is these forces means the gravitational force, okay, as well as the electrostatic force, both I am taking together. Okay, these forces, gravitational force and electrostatic forces, are central forces. They are central forces. Now what is the meaning of this central forces? Central forces means the force will act along the direction joining the two objects. Okay, so if you take the case of gravitational force, okay, it is between two masses, right? So when you join the centers of both the masses, and if you join them by a line, okay, then this force of gravity, gravitational force, will always act along the line. Okay, and the direction of this gravitational force is always towards the bigger mass m, towards the mass m. Okay, so if you take for example Earth as a bigger object, and if you take a person, okay, on the surface of the Earth, okay, as a small mass m, then this person will be attracted by force of gravity towards the Earth. Okay, so the person will be attracted towards the Earth. Okay, and actually the Earth is also attracted towards the person, but you cannot imagine of Earth moving closer to the person. Okay, you can think of person moving closer to the Earth. For example, in the Newton's case, when he observed the apple, okay, from the tree came down and fell on his head. Okay, so apple being a smaller mass, okay, it was on falling, it came towards the center of the earth. Okay, it came on the earth's surface. It was not the other way. The earth did not move towards the apple. Okay, so that is the simple logic behind that, right? So central forces will always act along the line joining the two masses. You cannot expect this gravitational force between these two being something in this direction or something in this direction. No. Okay, it will be always along the line joining the centers of the two masses in the case of gravitational force, right? In the case of electrostatic force, suppose you have two charges, okay, capital Q and small q, separated by some distance, say r, okay, and the force, in this case the electrostatic force, okay, will be always along the line joining these two centers of the charges. Okay, so when you join the centers of these two charges by a straight line, the electrostatic force either of attraction or repulsion will be along this line only. If it is repulsion, it will be along this line in this direction. Okay, if it is attraction, again it will be along this line only. So this is the meaning of central forces. Central forces, they always act along the line joining the two objects. Okay, in gravitational field, okay, the two objects can be two masses, and in electrostatic field the two objects are nothing but the charges. Okay, so q, capital Q and small q are charges, right? So that is about central forces. So both the forces are central forces, right? Next thing I want to talk to you about these two forces is both are conservative forces. Now this is very important property, conservative forces. Now what is the meaning of conservative forces? It's very important, right? So this gravitational force and your electrostatic force both are conservative. Now what is the meaning of conservative? Conservative forces means what? These forces, will not be path dependent. Okay, so conservative forces, a very important point is conservative forces, they are path independent, you can say, path independent. Okay, or in other words, you can say that do not depend or are not affected. You can say do not depend on the path. Okay. Second point about this conservative forces is work done. Any force will always do some work. Okay. So work done by conservative forces in a closed path, is always equal to 0. Okay, so these two properties about the conservative forces is very important. Let me tell you, explain you this property more in detail a little bit, so that it will help you further when I explain you the derivations of this field and the field strength and all that. Okay, so first of all, let me explain you what is the meaning of path independent. Now suppose this is a ground level, okay, and this is a level which is at a certain height. Say this height is, say, h. Okay, now you can imagine a person, okay, going from this height, the ground level height, to this height. Okay, you can imagine a person, okay, climbing from year to year. So you say that this particular person has covered a distance, vertical distance of h, but by climbing. Okay, so this is the path. Okay, now there is a monkey who just jumps from this level to this level. Okay, and this is the path described by the monkey, right? Okay, so there are two different paths. One is this one, okay, which is through the climbing the ladders. Another one is this one. This is directly, you are going from ground level to this level by directly jumping. Okay, fine. So the distance covered vertically is same in both the cases. So work done by both the path. Suppose this is path 1, this is path 2. By both the path, both path 1 and path 2, okay, will be same. Okay, work done by the gravitational force. Okay, gravitational force. Right. So if a person climbing from this point to this point, and if the same person, okay, going from this point to this point directly, okay, vertically, will be acted upon by a gravitational force which pulls him downwards, right? But despite of that gravitational force, okay, despite of a different type of the two paths, okay, the work done will be the same. Now this is happening because this is a property of a conservative force. This is happening because gravitational force is conservative. Okay, same way for two charges. Suppose you have one charge q1, you have another charge q2. Okay, and suppose this charge is or you have any one charge, right, q1. Okay, if you take this charge from a point A to a point B over here by two different paths. Okay, suppose you take it this way, A to B, this is path number 1, or you take it this way. Okay, this is path B, part 2 you can say. Okay, so either you go from A to B straight way along the path 1, or if you go from A to B along this path, okay, A to you can say A dash and then to B. Okay, if you go this way, in both the cases here also, in both the cases, the work done, in this case now it will be work done by the electrostatic force. The work done by the electrostatic force, okay, for both the path 1 and 2 will be same. This is a very important property of conservative forces, and this is happening again because electrostatic force is also conservative force. Okay, so gravitational force is conservative force and electrostatic force is also conservative force. Okay, fine. This was one property. Second property is, suppose a person goes from A to say B, okay, this way, okay, and he returns from B to A along some other path maybe, okay, or the same path you can say this way. Okay, so work done in going from A to B and the work done in coming back from B to A is always the same but opposite in sign. Okay, so work done from A to B is equal to negative of work done from B to A. This happens in the case of a conservative force. Okay, so the work done by the gravitational force Fg in going from A to B will be equal to minus of the work done by the gravitational force in coming back from B to A. So if you say what should be the work done, total work done in going from A to B and back from B to A, this is known as a closed path, or you can say the return journey. So if somebody is going from A to B and coming back from B to A along the same path or the different path also, okay, because it is path independent, right? Then the total work done by the gravitational force, okay, along the closed path. So what is the meaning of closed path in this case? It is from A to B and B to A. Going from A to B and returning from B back to A. This is known as closed path. Will always be 0. Okay. Or you can say the work done by the gravitational force in going from A to B will be equal to negative work done by the gravitational force in coming back from B to A. Suppose work done in going from A to B is say 100 joules. Okay, work done by the gravitational force in going from A to B is 100 joules. Then the work done in coming back from B to A by this gravitational force will be equal to minus 100 joules. Okay, this is the meaning of it. And the same thing holds equally good for electrostatic forces also. Okay, so that was the second property of conservative forces, which are very, very important according to me. So gravitational force and the electrostatic force, both being conservative, these two properties will hold good, or it will be obeyed by both these forces, right? Okay. And what else I want to tell you about these forces is, okay, gravitational force and this electrostatic force, whatever formula we have studied, okay, is applicable for point masses in the case of gravitational field or gravitational force, applicable for point masses in the case of gravitational force, and it is applicable for point charges. Okay, in case of electrostatic force. So when we are talking about gravitational force and electrostatic force, okay, and when we are using the respective formulas, that is Fg is equal to G, capital G, mm upon r square. Here Fe is equal to 1 upon 4 pi epsilon q, small q, divided by r square. When we are using these formulas, you have to see that this m, the masses, are point masses. Okay. Here your charges, that is q and small q, are point charges. Now what I mean by point masses or point charges is these masses or this charges, which we are talking about, has to be in the form of a small point. Okay. Or if you enlarge this, it can be in the form of a small sphere also, you can say. Okay. So either you call it a point or a sphere, it is considered as a point mass. In other language, what I mean by point mass is whenever the distance between two objects is very large. Okay, now take an example of a aeroplane. Okay. Now when you observe an aeroplane from a very closer distance, suppose you are at an airport, okay, and if you see the aeroplane either landing or taking off from that airport, okay, the size of the aeroplane will be very, very, very huge. Okay, and in that case, the uh, distance comparatively between yourself and the aeroplane will be very small. So suppose this is you who is standing somewhere on the airport, and there's a huge plane over here. Okay, right, this is a plane. So this is very huge mass. Okay, this is comparatively very less mass, and this distance is also very small. Okay, right, compared to when you are on the earth surface. And now if you see the aeroplane high up in the sky somewhere over here, you will be able to see the same plane but a very tiny object. Like, okay, here you will see it like a huge object, here you will see it like a tiny object, isn't it? Even the celestial objects like moon, Jupiter, sun, stars, all that in the sky that you see are actually very, very huge. Okay, but when you see from a very large distance, from say from the earth's surface, then this moon, star and all those, they will look smaller in size. Okay, so whenever comparative distance is very, very, very large, okay, then the objects can be considered to be as the point objects. Okay, so when I talk about point masses or point charges, this is what I mean. What I mean to say is the distance, that is the r, is very, very, very large, okay, compared to the size of the objects. Okay, when this is happening, we say that the object is a point mass or a point charge. Okay, so this is a very straightforward and simple understanding of a point mass. Okay, so on the earth's surface, if there are two objects, like here you can see one person and an aeroplane over here, you will not find any gravitational force. There is actually a gravitational force acting between these two, okay, because the law says that it has to be there. But then this distance being very small, okay, compared to the sizes of the objects, okay, the g value is in the order of 10 raised to minus 11. Okay, so this g, the constant, is having a very small value. It's in the terms of 10 raised to minus 11. Okay, so this is such a small value that the force, even though there is existing, the force of gravitational force is existing between these two objects, but you will not literally see them being attracted towards each other. Okay, or you cannot see that this man is automatically pulled by this aeroplane, something like that. No, you won't be finding that to happen. Okay, but in the case of long distances, these forces, you will be able to see the effect of these forces. Okay, so basically this was the point that I wanted to tell you about. Second and the last aspect of these forces is very important. The gravitational force is only attraction force. Fg is only attraction. Okay, you will never find that due to gravity one body is moving away from other body. Suppose this is m and this is small m, there will not be repulsion. Okay, so in the case of gravitational force, repulsion is not there, only attraction. Okay, so the attraction, and that too, the smaller body will be attracted towards the bigger body. So the force of gravity will be acting in the direction right to left in this case. Okay, because this is a smaller mass, this is a bigger mass, so the force will be acting from or it will be acting towards the center of the bigger mass. Okay, so the force will be in this direction, right? Okay, and there's only attraction force, right? So the field lines of this force can be thought of as going from here to here. Now this field lines can be from any mass in 360 degree. Okay, so you can make n number of lines to show the field lines of the gravitational force. Okay, so you can say the force, can be represented by these lines. Okay, all lines are going in the direction of the center of the bigger mass, right? This is small mass. Okay, in the case of electrostatic force, there is a little difference. Okay, here you will find both traction as well as repulsion. Now why this is happening? Because in the masses you don't have any two different type of masses. Either a mass will be bigger in size or it will be smaller in size. Okay, but in the case of charges, okay, you have two type of charges, positive and negative. Okay, positive and negative. So suppose you have two positive charges, say you have q1 and q2, two positive charges. Okay, and they are separated by some distance, say r. Okay, then the force between these two charges will be a force of repulsion, because the law says that like forces repel each other. Charges, they repel each other. Okay, and this being both plus plus, they will repel. Okay, same case if it is minus q1 and this is minus q2, again separated by some distance, say r, again there will be repulsion, because still they are like charges, both are negative. Okay, so like charges repel. Okay, getting me? Like charges, they repel. And in the case the charges are alike, suppose one charge is positive q1, another one is negative q2, and they are separated by some distance r. Now in this case, because the two charges are unlike, so unlike charges, they attract towards each other. Okay, so there will be a force of attraction. Got it? So let us try to understand this more clearly. Now suppose this is A and this is B, Q1 and Q2. Okay, or let it be Q1 and Q2, no issue, because we have mentioned two different letters, 1 and 2. Okay, so in this case, you see there is a repulsion. Now what happens, the norm is to represent the force, electrostatic force, okay, acting on q1 due to q2. Okay, acting on force acting on q1 due to q2. So q1 you have to write first, and the cause, which charge is causing this particular repulsion, that you are going to write second. Okay, so as q1 q2, the meaning of this is the force acting on q1 due to q2 will be in this direction. Okay, so what will there is repulsion. Okay, so this will go in this direction, right? Are you getting me? Okay, and same way, suppose if you write f q2 q1, this will mean the force acting on q2 due to q1. This force will be in this direction. Okay, so can you see q1 is throwing this q2 back, okay, or it is repelling q2, and q2 is repelling q1. You get me? Same way here, when both the charges are negative, fq1 q2 will mean the force acting on the q1 due to q2. So this is q1 and this is q2. Okay, so q1 will be thrown back. Force acting on q1 because of q2 will be in this direction, and force acting on q2 because of q1 will be in this direction. So can you see that both, whether the charges are both positive or both negative, okay, the repulsion is taking place. Okay, both charges will move away from each other. But when the charges are unlike, one is positive and one is negative. Okay, so F Q1 Q2 means the force acting on Q1 because of this Q2. Now what this Q2 will do? It will move the force, move the charge Q1 in this direction, isn't it? So F Q1 Q2 will be in this direction, right? And same way F Q2 Q1, that is the force acting on this charge Q2 because of Q1. Sorry, this is Q1. Okay, so force acting on this Q2 because of Q1 will be in this direction, isn't it? So can you see both are attracting towards each other, right? So if you follow this norm, okay, you will understand that like charges, they are going to repel each other, and unlike charges are going to attract each other. Okay, so this was all about the forces, electrostatic forces and the gravitational forces, the similarity between them and the concept. And in the process you have seen that both concepts are almost similar, and that is why I made a point to go for a simultaneous study of both the forces, gravitational force and electrostatic forces. Okay, so now you must have understood the basic of both this gravitational force and the electrostatic force. In the next video, that is part 2, I am going to deal with some numericals based on both the forces. Okay, that is the gravitational force as well as the electrostatic force. Only the numericals related to the force concept. Okay, and let us see how we can handle that those numericals on the basis of whatever we have studied in this particular video, the concept about the two forces. Okay, so that's all for today. In the next series, I'll be coming up in this series, in the next part, I'll be coming up with the numericals on these two forces, and after that, I'll be still moving ahead with whatever similar properties or whatever similar concepts I find between this gravitational and the electrostatic fields. Okay, and we'll proceed in the same way, right? So that's all for today. I hope you must have liked this video. Okay, and let us see how it works. Fine, thank you very much.